So starting off, we're looking at planes and lines in 3D. So remember, plane's just a flat surface in 3 dimensions, obviously line, straight line. There's 3 things that can happen with a line and a plane. First thing is that your line doesn't cross your plane. So if the line is parallel to the plane, it doesn't cross it. So imagine the floor is a plane and you've just got a straight line going along the street. It's not going to cross that. Okay. In which case, there are no solutions if you try and find the point of intersection. You could also have that the straight line was completely included in the plane. So that would be if our line was along the floor, much like the edge of this room or something. In which case, there are infinitely many solutions. There are infinitely many points that lie both on this line and in this plane. Or, more often than not, you can have one point of intersection where your straight line just crosses the plane once. So a straight line going at an angle down through the floor will just cross once here, and there's one unique solution. So there's 3 things there. So we're going to look at way 3 on there, where a straight line crosses the plane and finding the point of intersection. It's very similar to what we do with 2 lines meeting, in that you substitute the equation of the line into the equation of the plane and just solve it. Let's have a look at example. Sorry, Jess.
So like comes in from like behind it and then comes out from the front. If it has solution. Yeah.
So in the example here, we've got given an equation of a straight line. So 1, 2, 1 plus lambda times 4, 1 minus 3. Now I've got the equation of plane in normal form. It's easiest if it's in scalar product form or normal form like that. And what we're going to do is substitute the equation of the line into the equation of the plane. I'm going to do that by kind of smushing this equation of the line together. So I've got 1 plus 4 lambda. I've got 2 plus lambda, sorry, from j. And I've got 1 minus 3 lambda. Okay. I'm going to substitute that into the equation of the plane instead of r. So I've got 1 plus 4 lambda, 2 plus lambda, 1 minus 3 lambda, dotted with 3 minus 1, 2 is equal to 30. And you do this dot product, you'll get an equation for lambda, which you can work out lambda, and then substitute it back into your equation of your straight line to work out the point of intersection. So do this dot product, multiply across, so you get 3 times 1 plus 4 lambda, usually 3 plus 12 lambda. 2 plus lambda times minus 1, so minus 2 minus lambda, and 2 times 1 minus 3 lambda, 2 minus 6 lambda, which equals 30. Collect up your lambdas, collect up your numbers. So 12 minus 1 is 11, minus 6 gives me 5 lambda. Taking my numbers across, take the 3 across, that gives me 10, and I've got minus 2 and plus 2, which cancel. So I get 5 lambda equals 10. So the line and the plane intersect when lambda equals 2. Don't forget to go back and substitute this into your equation of your straight line to work out point of intersection. So if you stick in lambda equals 2, you get 9, 4, minus 5. Technically, this is a position vector, and the question asks for the coordinates. Right, as a coordinate. So if you can remember back to the first vectors pack, there's a dot product formula which has got cos theta in it, which we use to find angles between 2 lines. So the formula is A dot B, magnitude of A, magnitude of B, cos theta. And obviously you can rearrange this to make cos the subject to work out the angle between 2 lines. Now, for the angle between a line and a plane, what you actually do is you find the angle between the direction vector of the line and the normal vector of the plane. Okay, so put that. Find angle between direction, the line, and the normal. Okay, so that's what this diagram is saying here. So you imagine this dotted line is your plane, this is your normal vector, and this is your line. The angle you're trying to find between your line and your plane is this one. But what we usually prefer to do is find the angle between the normal and the line, and then you've got to take it away from 90. Okay, that's what I always do. I just remember that I work out the angle to take away from 90. I don't actually like that diagram. No, I don't like any of the diagrams.
Very into diagram now.
I think that what makes more sense to me anyway is this. So here's my plane. I'm doing the angle between straight line and a plane. It is this one that I'm trying to find out here, so I'll call it. Okay. What I'm actually going to do is find the angle between the normal vector and the line, which we call alpha, and then to work out theta, I take it away from 90. I think it makes more sense that way than the diagram that's in the back. Okay. This isn't something that we really mention in A-level maths, but I might touch on it briefly. Yeah. It's not integrated. So it turns out that because sine and cos graphs are translations of each other, you can write them in terms of each other. And it turns out if you're doing 90 minus an angle, that's cos of 90 minus an angle is the same as sine of that angle. So there is a formula for this where the cos turns into a sine. I don't use it. I don't really like it, but if you want to, I'll give you it there. Yeah. So this formula is only for finding the angle between a line and a plane. What I prefer to do is just use the dot product formula and then take my answer away from 90, but it's up to you what makes more sense. Only used for finding the angle between a line and a plane.
Joel's thinking so.
So
What about?
let's have a look at this question here. So determine the angle between this line and this plane. First off, I'm going to convert these both into vector forms. Specifically, I'm going to put this into normal form because it's not really useful in Cartesian. Okay. So converting the equation of the line, remember what you do is you set each of these bits equal to lambda, but you can kind of skip this step if you want, but just to demonstrate. So you set each part of the equation line equal to lambda. You rearrange to make x, y, and z the subject. So I times it by 2 and add 1 to this one. I just minus the 1 across for y. And just times it by 2 for z. And then to put this into straight line form, your x, y, z goes in a vector, that's just r. Your numbers go in a vector, so you've got 1, minus 1, and 0 from the bottom one. And then you've got lambda times 2, 1, 2. So you can skip straight to that if you want. Just showing you whether, reminding you whether. The important part is that we want the direction vector of this line. So this is the bit that we're going to use. Okay. For the plane, I've got it in Cartesian form. I want it in scalar product form. So I can look at the coefficients of x, y, and z to get the normal vector. So it's 1, 1, there's no z, so the coefficient of z is 0. And if I take that 1 across, it will be equal to 1. So we can just write that down. The important bit about this that I want is the normal vector. So I'm finding the angle between the direction vector of the line and the normal vector of the plane. So I'm going to use the dot product formula. I'm going to use cos theta equals A dot B. Magnitude of B. So if I do 2, 1, 2 dotted with 1, 1, 0, I get 2 plus 1 plus 0. I get 3. If I do the magnitude of 2, 1, 2, so it's just Pythagoras in 3D, so 2 squared plus 1 squared plus 2 squared gives you root 9, so there's 3. Magnitude of the second one, 1 squared plus 1 squared plus 0 squared. Root. I can stick all this into the formula now for cos. So I get cos theta is 3 over 3 root 2. Inverse cos of that, do it in your calculator, you'll get 45 degrees. But actually, in this case, if you minus that off 90, you still get 45. But I'm going to write it at the end. Okay, so the angle between the line and the plane in this case is 45 degrees. Usually, it will want the acute angle. What you can do is you can put modular signs around this, like modular signs around this. That will always give you the acute angle if you make that positive. So it's if you end up with A dot B being negative, you can just make it positive and you get the acute angle, or you can just get the obtuse one and take it away on it. Can I get you to have a go at the U try? It's a bit nicer because they've given you it in the proper form style. Okay, so here's what you should get for this one. So you're doing it on the direction vector and the normal vector. So it's 2, 6 minus 3 and 1 minus 2, 3. Work out the magnitude so that you get 7 and root 14. Work out the dot product so that you get minus 19. You can make that positive so that you ensure that you get an acute angle if you want. And then I would have done cos of that and then take it away from 90 because that's just the dot product formula. But you can use this when you can use sine and you'll just directly get the answer. Over the page is finding the angle between two planes. Now we'll justify this, but ultimately it just boils down to finding the angle between the two normal vectors of the plane. That will give you. Here's what we're doing now. So we're finding the angle between two intersecting planes here. So there's obviously there's 2 options. There's either this obtuse angle in here, this one, or there's an acute angle between them in here. By using kind of what you know about quadrilaterals and opposite angles and stuff. So what you've got here are the 2 normal vectors to the plane. These will extend up here, and I can draw a quadrilateral in the dodge side of the bottom. The normal vector is perpendicular to the plane. So these 2 angles in here are 90, and you know there's 360 degrees in a quadrilateral. So this angle and this angle must add up to 180. Okay. And also this angle and this angle are on a straight line, they also add up to 180. So this angle at the top of the quadrilateral there is theta. I don't know why they've got that one up there. Okay. So all you need to do, oh no, I do know why. All you need to do is you need to find the angle between the 2 normal vectors, and that will give you the angle between the 2 planes. So I've justified it, but you don't need to justify it in the exam. In here, we're just going to use the normal dot product form. I'm going to put modular signs around the whole thing because, again, usually you want the acute angle, and if you just make your answer positive, you'll end up with the acute. Okay. That's kind of why I prefer to just remember one formula and just remember to minus it from 90 for line of the plane, but it's up to you if you prefer to remember more formulas. So this example, finding the acute angle between these two planes, I'm finding the angle between these two normal vectors. So this one is my A, this one is my B. So if I do modulus of A, that's 2 squared plus 2 squared plus 3 squared. Root 17. Modulus of B is 3 squared plus 3 squared plus 1 squared. Root 19. And I need A dot B. 2 minus 3 dotted with 3 minus 3 minus 1. Gives you 6 minus 6 plus 3. So I get stick all this into the formula. So cos theta equals A dot B, which is 3 over modulus of A modulus of B. I didn't need to put those modulus signs on because it is positive anyway. It is 80%.
Work at home and it just turned off my focus. This interesting.
That's it. You don't need to do anything with it. It's just 80%. Do the U-type for me, please. All right, so you should get 79.9 for this one, which I think most of you did get.
Everyone's right. No relationship is safe.
Okay. Lovely. And not so much anymore. Used to read.
Oh, no,
Now I have children.
Lots of people.
Yeah, but that's usually like liquor color.
No, we're gonna say it. So it's in the book like we used to start in that.
Yeah. We could get them like. I don't know. So. Like, you know, check that next.
I like the teen fiction section of
Oh, yeah. Yeah.
like Hunger Games.
Yeah.
Yeah.
I don't know. I don't mind Hunger Games. I didn't say nothing.
All right, last example. Thank you. Guys, thank you. So this question says these two planes are perpendicular. Find the possible values for K. If the planes are perpendicular, it means that their normal vectors are also perpendicular. And remember, perpendicular means that the dot product is equal to 0. Normal vector of the first plane is 1 minus 3 minus 2. The normal vector of the second plane is K squared K2. So just do the dot product of those and set it equal to 0. I can work out what K is. So do the dot product of those. So 1 times K squared plus minus 3 times K plus minus 2 times 2. Gives you that. It's quadratic in K, which you can solve on your calculator. Or you can factor it there. And you get 2 values. Okay. I've got that. Put into that.